Let's talk about what you need to know and don't need to know for your final. I noticed for McDonough's class, L'Hopital's rule will not be on the final, right? He said that in class, I think, just on Wednesday. For Grosvenor's class, if you look at his website, specifically, yeah. So I was looking at his website. So if you look at his website here for a moment, oh, that's interesting. So we look down here, if you scroll down a bit to the final exam information at the very bottom, got to be lovely if it was larger. That's fine. I guess I can read that. So it's got the information, right? So it's got the time, place. So your final exam for Grosvenor is Monday at 1 p.m. There is a review session on Sunday at 1. There's an extra office hour on Friday. Material covered on the final. Functions: odd, even, one-to-one, composite, continuous, differentiable. Limits: asymptotes, continuity, derivatives, first, second. Tangents: velocity and acceleration, derivative rules, implicit differentiation, related rates, maxima and minima, first and second derivative tests, concavity, curve sketching, applied optimization problems, L'Hopital's rule. Also expect some theoretical questions, like, for example, on applications of the mean value theorem, intermediate value theorem, etc. So he's spelling it out for you if you're in Grosvenor's class, right? Those are the topics you are responsible for, which is most everything. Notably not in there. I don't see the limit definition of the derivative. I don't see delta epsilon proof. I mean, I suppose those could be still, I mean, I guess he said the limit, so I guess technically, right? But I feel like he would be more explicit if he meant that. You might still ask if you're in his class. Similarly, you might ask McDonough if there are specific things that won't be on your exam, like delta epsilon proofs, like the limit definition of those are the two things that I usually, when I've taught classes like this and actually been the instructor of record, I've asked those things on the first exam and then not asked them on the final, because it's like, we were done with that, we've moved on, but they could ask them. There's something, oh, and then and he did also provide a practice final, which I looked at. It looks challenging for sure. Not unreasonable by any means, but that's pretty typical. Let's go ahead and kind of, I think for ourselves, it'd be worthwhile to talk about the things that you should expect to see. And then if you want, we can do some practice problems. And really, honestly, what I'm doing to see this is I'm just looking at the syllabus for the class. In fact, I feel like something you all should be aware of as well is for any class in the math department, if you go to the math department webpage, and you click on courses, and you go down to syllabi, and then you click on, if you scroll down, undergraduate lower division syllabi, and you look at math 21A, it shows you what the department thinks should be spent on each topic. So, right, like 1.5 lectures on continuity, 1.5 lectures on limits involving infinity, and so on and so on and so on. So you can look at this to kind of give yourself an idea for 21B, right? So you might I see some surprised faces, like, yeah, there's some things on here that you might not have gotten to. Some people are better at covering all the things than other people are, which, that's interesting. Just came on all by itself. That's all right. Well, great. That's fine. It's weird. Anyway, so this is what you could, like, this gives you a general idea of what you might see. So just to kind of go back here for a second, look at 21B, just so you all can start thinking about next quarter. Right, here we go. So it starts off with antiderivatives and then area and then summation notation and so on and so on and so on. So it might be worth looking at once you're done with this quarter. Cool. What else before we get into it? Next week, office hours. All of our office hours for the math specialists are in math drop-in in the library. We will be there. There'll be at least one specialist there every day, Monday through Thursday from 10 to 3. I posted my office hours on Canvas. I think it's every day from 10 to noon and 1 to 3, except for Monday. It's only 10 to 11, 1 to 3. So yeah, that's all the information I can think of that might be necessary for next week. What day is, I know Grosvenor's finals on Monday. What day is McDonough's final? Wednesday? Okay. All right. So let's briefly talk about what we should be aware of. And I'm really just looking at the syllabus here. So chapter one, I mean, I feel like the chapter one stuff is kind of embedded in everything else we've done. So let's move on. So let's see. So I would say if we need to know how to find tangents and tangent lines. When I say tangents, I mean like slope. Yeah. Oh, you might want to see the thing. Fair enough. Where'd it go? Good question, James. Cool. There you go. Limits, the usual kind of stuff. I imagine that. There was one. There was one other thing on Grobner's thing that I saw, which was that he wrote that the majority of his exam material will be coming from chapter 4. I don't know if that's true for McDonough, but certainly that's what Grobner did write on his final exam info. So just something to be aware of. Limits. So limits, there's all kinds of stuff. There's a lot of 0 over 0 types. There's infinity over infinity types. There's the usual algebra stuff. Again, right, I'll point out that for McDonough's class, no L'Hopital's rule. So anything that's a 0 over 0, infinity over infinity is something you're gonna have to deal with in the usual ways we've dealt with before, which is factoring and canceling, or if it's an infinity over infinity, typically dividing everything by the highest power of x in the denominator. I don't think the precise definition of a limit will be on there. But and so when I say precise definition of a limit, that's just another way of saying the delta epsilon. But really, you should ask. And most people will tell you if they're going to ask you a delta epsilon question or not. I suppose also in the limit section, one-sided limits are also fair game. In my mind, these typically mostly come up, for example, like the limit as x approaches 2 from the right of 1 minus x over x minus 2. When you plug that in, you get -1 over 0, but it's a slightly positive denominator because a number bigger than 2 minus 2 is a little bit positive. So that limit's going to be negative infinity. Not that you can't look at one-sided limits in other contexts, but to my mind, that's the usual place where we see one-sided limits specifically popping up. Continuity. I definitely imagine continuity will show up somewhere on your test. To show something's continuous at a point A, you have to show 3 things. You have to show that 1, f of A exists. 2, the limit as x approaches A of f of x exists. Usually this means showing the left and the right-hand side limit are the same. And finally, putting it all together, that these are equal to each other. That f of A is equal to the limit as x approaches A of f of x. And I will just say, as I always say, you could really just boil this definition down to the last part here. This is all that needs to be true because these 2 things have to be true for the last thing to be true. But we typically think of it this way, so it's easier to kind of digest and work through. And then we have derivatives. I feel like I started the derivative section in the wrong spot. There's so much to say about derivatives. There's a lot to say, right? So, I mean, when I think about derivatives, the first thing that comes to my mind is, what does a derivative mean? Derivatives, the rate of change. It's how, if you're writing dy dx, it's how y changes as x increases. And then there's all sorts of things. So this is where I'm actually going to start, right? So I feel like this stuff up here, okay, whatever. But as far as derivatives, we have our differentiation rules. So we have the product rule, Let's not start with the product rule, James. Let's start with let's go more. We have the power rule. The derivative of x to a power is that power times x to the one less power. We have, okay, we have the constant multiple rule. So you take the derivative of a constant times a function. What does that constant do? What do I like to say it does? Hangs out. Constant hangs out, and you get c times the derivative. I will point out you could use the product rule if you wanted to. It's more work, but if you think of this as the product rule, it's the derivative of c times f of x, regular f of x, plus c times the derivative of f of x. But the derivative of a constant is 0. So this whole part's 0, and you just get the c times f prime of x. So that's why we abbreviate this rule. We don't typically think of it as the product rule, although you could. And then we have the product rule, which is that the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. We have the good old quotient rule, which to me feels very similar. It's the derivative of f of x divided by g of x, and it's equal to f prime of x times g of x. Although you know that whenever I do it, I say it as the bottom times the derivative of the top. So I'm thinking of it as g of x times f prime of x, same deal, minus the top times the derivative of the bottom, or f of x times g prime of x, all divided by the bottom squared, g of x squared. And finally, we have the chain rule. The derivative of a composition, f of g of x, or as I would say, f of some stuff, is the derivative of the outside function. You leave the inside stuff alone, and then you multiply by the derivative of the inside stuff. Are there any rules we've forgotten? I can think of one, but it's kind of a rule that we use all the time that we don't really think about using, which is the addition subtraction rule, where if you take the derivative of two functions added together, you just take each derivative and you add the results together. Which I think we do all the time. And of course, it can be addition or subtraction. So the derivative of f plus g is f prime plus g prime. The derivative of f minus g is f prime minus g prime. And I think that's a pretty comprehensive list of all the rules for differentiation. There's still some functions we need to talk about how we differentiate them, but these are all the rules. So, in fact, let's go to the next place. Yeah. Let's talk about all the functions we need to know how to differentiate. So, my mind, there is powers, which you already talked about. So, like for example, the derivative of 5x to the fourth is 20x to the cube third. It's an example of the power rule, and I suppose also the constant multiple rule in play. But then we have trig functions, exponential, logarithmic. That's about it. As far as types of things we have to be able to take the derivative of. There's still a few other applications like implicit differentiation, but using that, you're still using all the rules we've already talked about. So let's talk about the functions we have to be able to differentiate. Let's go trig first. So for the trig functions, the derivative of, how do I write this? Yeah, I'll write it that way. So the derivative of sine of x is equal to cosine of x. Now, when you see this, I want you to also be thinking of the chain rule version. In fact, I might just write down with them. The derivative of sine of x is cosine of x, which means the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. A typical way of writing this would be the derivative of sine of u, where u is our stuff, is equal to cosine of our stuff times the derivative of our stuff. So there's a chain rule version of this. where I'm thinking of U is our stuff. Or U is a function of X. And it's pretty typical notation. I think this is how the book usually writes the chain rule, is where they imagine U is the function of X. And then the other 5. The derivative of cosine of X is equal to negative sine of X. So the derivative of cosine of some stuff is negative sine of the stuff times the derivative of the stuff. The derivative of tangent of X is secant squared of X. And the chain rule version, the derivative of tangent of U is secant squared of U times the derivative of U. And then we have all the reciprocals. The derivative of cosecant of X is negative cosecant of X times cotangent of X. The derivative of cosecant of some stuff is negative cosecant of stuff times cotangent of the stuff times the derivative of the stuff. Similar for secant. The derivative of secant of X is secant of X times tangent of X. The derivative of secant of U is secant of U times tangent of U times the derivative of your stuff, which is U prime. And finally, the derivative of cotangent of X is negative cosecant squared of X. The derivative of cotangent, I should be slightly more explicit here. The derivative with respect to X of cotangent of U, a function of X, is negative cosecant squared of U times the derivative of U. So there's all the trig derivatives and their chain rule variants. Every function has a chain rule variant. You just replace X with U, and then at the end of the day, you multiply by the derivative of U. Or you replace X with your stuff, and at the end of the day, you multiply by the derivative of your stuff. Okay, so aside from trig, we also have exponential and logarithmic functions. There's kind of 2 things I think about. So exponential. So we have that the derivative of e to the x is equal to e to the x. And then the chain rule version, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then we also have a version where our base is not e. Although it comes up less often, it does come up occasionally. So we have that the derivative of a to the x, where a is some positive number that's not 1, is a to the x times the natural log of the base a. And similarly, there's a chain rule version. The derivative of a to the u is a to the u times the natural log of a times u prime. So for example, if I wanted to find the derivative of e to the x squared plus 7, it'd be e to the x squared plus 7 times 2x. Versus if I wanted to find the derivative of, say, 4 to the x squared plus 7, it'd be 4 to the x squared plus 7 times natural log of 4 times 2x. And then we also have the logarithmic derivatives. I should be careful. The logarithm derivatives. I say logarithm because there is also a process of logarithmic differentiation, which we have talked about. So for the logarithms, the derivative of the natural log of x is 1 over x. The derivative of the natural log of some stuff, I like to write it as 1 over the stuff times the derivative of the stuff, but a lot of people prefer to just write it as 1 fraction, the derivative of u divided by u. They're both the same, just matter of preference. And then we also have versions where the base is different. We have the derivative of the log base a of x. It ends up being 1 over x natural log of a. And similarly, if it was log base a of some function of x. It's gonna be 1 over our stuff times natural log of a, and then multiply by the derivative of our stuff. Or again, if you prefer, you can write it as one fraction, u prime over u times natural log of a. Okay. Oh, there's one more list of things we have to talk about for rules. Functions we not need to, oh my God, words. There's one more category of functions we need to know how to differentiate. And those are the inverse trig functions. I know I'm kind of skipping around the syllabus here, but I feel like this is a good place to like say all the derivatives. And we also have inverse trig. In my mind, you only have to remember 3 of them. Maybe even only 2, actually. So here's the 3 I think you need to know. The derivative of the arc sine of x is 1 over the square root of 1 minus x squared. The derivative of arc tangent of x is 1 over 1 plus x squared, or x squared plus 1, whichever way you want to write it. It's the same. And you might need to know, you might not need to know, that the derivative of the arc secant of x is 1 over the absolute value of x times the square root of x squared minus 1. Or depending on the class, maybe it's 1 over just x times the square root of x squared minus 1. If your teacher is asking about this, they will have need to have specified which version they want you to give them, because it's based on the choice that you have to make. Why do I think you only need to know these 3? Because the other 3 are immediately findable if you know these 3. I'm getting out of order here. 1 second. Okay. So if you know these 3, then you know the other 3. The derivative of the arc cosine of x, or you can write inverse cosine. I always like the arc notation. It's just as good to write cosine to the -1 of x, or inverse cosine of x. That's going to be negative 1 over the square root of 1 minus x squared. And the derivative of the arc cotangent of x is negative 1 over 1 plus x squared. And the derivative of the arc cosecant of x is negative 1 over the absolute value of x squared of x or minus 1. Or maybe, if depending on how they've done it, negative 1 over just x times the square root of x or minus 1. Those are all your inverse trig derivatives. I didn't write down the chain rule versions of them. I think you know how that works by now. I'll write down 1. So write the derivative of the arc sine of, actually I'll write down 2 of them because fine. Arc sine of u would be 1 over the square root of 1 minus u squared times u prime. I know, that's fine. Right, so whenever it's a chain rule version, you're just replacing every x with the stuff, and then at the end, multiplying by the derivative of the stuff. Most of the time, that means replacing 1x with whatever your stuff is. But in a few special functions, there are 2 things to replace, specifically the derivative of secant. If you go back here to the trig functions for a second, the derivative of secant and cosecant, there are 2 places where you have to put in the stuff. Derivative of secant of u is secant of u times tangent of u, and then u prime. Same deal for cosecant. For cosecant, it's negative cosecant of u times cosecant of u times u prime. And interestingly, it's also true for the inverse secant and the inverse cosecant. Right? You'd have 2 x's there. So, for example, if I was going to do the derivative of the arc secant of some stuff, it'd be 1 over the absolute value of the stuff, square root of the stuff squared minus 1, and then times the derivative of the stuff. Okay, and I think those are all the functions you have to be able to differentiate. Oh yeah, of course. Yeah, sorry. Oh, geez, what did I do there? Sorry, I pressed the button. Geez. Okay.
Why don't you differentiate both views for arc-secant like they
Well, so that's a fair question. So let's actually look at a couple of examples. So, and I want to go back to secant for a second, but we'll talk about arcsecant too. So let's say I wanted to find the derivative of the secant of x cubed plus e to the x. So here's the way I'm always saying it in my head. I'm saying the original rule first. The derivative of secant of x is secant of x times tangent of x. Both those x's are just x's. So then the derivative of secant of some stuff is going to be secant of the stuff times tangent of the same stuff. And then we have to multiply by the derivative of the stuff, which is 3x squared plus e to the x. I suppose if you really wanted to, I don't love doing this, but you could write this as a composition of functions. It's not my favorite, but you could do something like, I'm going to say f of x is secant of x. And g of x is the inner x cubed plus e to the x. And then we know that the derivative of f of g of x is f prime of g of x times g prime of x. Okay, well, f prime of x is secant of x times tangent of x. F prime of something different, g of x, is secant of g of x times tangent of g of x, which is secant of that times tangent of that. So here we're going to get secant of g of x times tangent of g of x. So right there is my, we're not done. Right there is my f prime of g of x. And then we have to multiply by g prime of x, which is 3x squared plus e to the x. I can't emphasize strongly enough. If this stuff, if the derivative of the stuff out here has more than one thing added together, like it's 2 or 3 or multiple things added or subtracted together, you have to put it in parentheses. Otherwise, it is not correct. Because if you don't have parentheses here, it looks like it's all this times just 3x squared, and then after that, you're adding on e to the x, which is not what we actually mean. So make sure that your derivative of your stuff has parentheses around it, if it's not like an enumerator or something. So then to do an example more like what you asked about, if I wanted to find, say, the derivative of the arc secant of, how terrible do I want this to be? Not that terrible, really. Let's say x e to the x. Let's say x squared e to the x. Well, just like before, I can think of this as an f of g of x, where f of x is the arc secant of x, or if you prefer, f of u is the arc secant of u, if you want to write it that way. Doesn't actually really matter. And g of x is the inside x squared e to the x. So then, oh, sorry, I wrote something wrong here slightly. The derivative of arc secant of x squared e to the x should be the derivative of f of g of x. And that should equal f prime of g of x times g prime of x. We know that the derivative of arc secant of x is 1 over the absolute value of x times the square root of x squared minus 1. So then, if that's my derivative when I plug in x, my derivative when I plug in g of x is going to be 1 over the absolute value of g of x times the square root of g of x squared minus 1. And then we multiply by g prime at the end. And then plugging in what g and g prime are, I'm going to get 1 over g, which is, sorry, the absolute value of g. I will point out here, a lot of the times if you see people write this, they're going to drop the absolute value there because x squared e to the x is already always positive. So the absolute value is unnecessary. but not wrong to write if you want to write it. And then we'd have the square root of x squared e to the x squared minus 1 times the derivative of x squared e to the x, which requires the product rule. It's 2x e to the x plus x squared times the derivative of e to the x. So hopefully that better explains why we're getting that inside part showing up in both spots. And it's really because we've got, sorry, in our derivative of the arcsecant of x, we've got that x showing up in 2 spots. So we're just replacing that x with the insides. But yeah, arcsecant and regular secant are kind of atypical in that way, in that the inside argument of the function shows up twice, as opposed to really anything else we deal with where it does not. I should say anything else other than cosecant and arccosecant, right? Those also have the same sort of thing. Okay. I suppose there's one other thing we have to be able to differentiate, even though it's not like it's not a new derivative to be able to do, but it is a method of differentiation that we definitely talked about, and that is logarithmic differentiation. I'm going to write this problem in the worst way possible. I'm going to write find the derivative of, let's say, let's make it, ooh, yeah, that's fun. Let's not make it that bad, James. Let's make it x to the, let's make it x squared plus 1 to the x cubed plus 2 power. So you have an f of x to a g of x, a function to a function. There isn't a, I mean, that's not true. There is a terrible formula you could learn and remember. You should not even think about memorizing the formula here. It's terrible. It's awful. The reason why the way I have written this is extra terrible is because it's hiding something that you need to do to make this work. You need to write y equals your function so that you can take the natural log of both sides and then bring the power down. Most people won't write this way. Most people will write it as find dy dx, or the derivative of, for y equal to x squared plus 1 to the x cubed plus 2. And then it's a little more obvious that, oh yeah, I can take the natural log of both sides. But if someone wrote something like this, it's perfectly fine to rewrite, say, okay, I've got y equal to my thing, then I'm going to take the natural log of both sides. And it's kind of, it's not the only way, but it's really the only way to go here. So take the natural log of both sides. The whole purpose of taking the natural log of both sides is it allows us to bring that exponent down in front. So we can rewrite this as the natural log of y equal to x cubed plus 2 times the natural log of x squared plus 1. Now we differentiate both sides. We know that y is a function of x. Even if it wasn't, we'd still assume it was. So then we differentiate the left-hand side. We're going to get 1 over our stuff times the derivative of our stuff, or 1 over y times y prime. On the right-hand side, we're going to have to use the product rule. Derivative of x cubed plus 2 is 3x squared times the other thing left alone. Plus, now we leave the x cubed plus 2 alone, and we multiply by the derivative of the natural log of some stuff, which is 1 over the stuff times the derivative of the stuff. So 1 over x squared plus 1 times 2x. I would really recommend doing these next 2 steps in one. So here are the next 2 steps condensed into one. I will go back and fill in the missing step in a second. So I'm going to multiply both sides by y. I'm also going to replace y with what it's equal to. So y is equal to x squared plus 1 to the x cubed plus 2. So when I multiply both sides by y, I get y prime equal to y. There's my y. Times all that. 3x squared times natural log of x squared plus 1. And I might do some very mild simplifying here. I might write the next fraction as 2x times x cubed plus 2 over x squared plus 1. You might even multiply at the top as 2x to the fourth plus 4x, but I really don't feel like I need to. And that's my answer. The intermediate step that I am skipping because it's just so tedious to write this out both times is to write it as y prime equal to just y times all that stuff. And then in the next step, you replace y with what it's equal to. But I think you can skip this step and just go straight to that step, which is fine. Okay. Other things in chapter 3. We have implicit differentiation, which we just saw an example of. I mean, albeit a very mild example where it wasn't really that crazy. So implicit differentiation. I would expect to see something, right? So that's where you have x's and y's all mixed up and you differentiate everything, assuming y is a function of x. There's two varieties of these questions typically. There's one variety, so type 1, where they say, great, for the following equation, x cubed plus 4xy squared equal to tangent of y. Sure. Find dy dx. That's one type of question we might ask. The other type is something like, I'm going to be a little more careful with my numbers here. Given something like, sure, x plus 2y to the fourth plus 3x squared equal to, let's see here. One second, let me think about the numbers for a minute here. Sure, equal to y to the third plus 4x plus 5. Sure. Find the equation or just slope, but usually equation of the line tangent at the point 2, -1. And although they both start off the same, they go in somewhat different directions here. Let's look at how we do the first one. So the first one, start by differentiating both sides. So you're going to get 3x squared plus, we have to use the product rule here. So I'm thinking of this as 4x times y squared. The derivative of 4x is 4. Leave the y squared alone. Plus 4x times the derivative of y squared is 2 times y to the first times the derivative of y equal to the derivative of tangent of y is secant squared of y times y prime on the outside. Questions about this? After we have differentiated both sides, the rest of this is some algebra. We're collecting y primes on one side, dividing out whatever's left over. So I'm going to collect my y primes on the right since there aren't any not y prime terms on the right. So I'm going to have 3x squared plus 4y squared equal to secant squared of y times y prime minus 4 times 2 is 8. So let's say 8xy y prime. Factor out the y prime. So 3x squared plus 4y squared equal to y prime times secant squared of y minus 8xy. And finally, divide by that to get y prime equal to 3x squared plus 4y squared divided by secant squared of y minus 8xy. The other type of implicit differentiation problem starts off the same way. We're still going to start by differentiating both sides. But then instead of solving for y prime algebraically like we did here, we're going to immediately plug in the point of tangency to find the slope of the tangent line. Let me show you what I mean. So the next one, we're given x plus 2y to the fourth plus 3x squared equal to y cubed plus 4x plus 5. And we want to find the equation of the tangent line at the point 2, comma -1. So we start off by taking the derivative of both sides. The derivative of some stuff to the fourth is 4 times my stuff to the third times the derivative of the stuff. The derivative of x is 1. The derivative of 2y is 2y prime. Plus the derivative of 3x squared is 6x equal to the derivative of y cubed is 3y squared times y prime. The derivative of 4x is 4, and the derivative of 5 is 0. But then after that, you plug in x equal to 2, y equal to -1, and you solve for y prime. So doing that, I'm going to get 4 times 2 plus -2 to the third times 1 plus 2y prime. I should be smart about this. 2 plus -2 is 0. 0 to a power is still 0 times all this other stuff. All that's going to be 0 by design. Plus 6 times 2 equal to 3 times -1 squared times y prime plus 4. So 12 minus 4 is equal to 3y prime. So 8 divided by 3 is equal to y prime. We're not quite done because the question asked us to find the equation of the tangent line. So we're going to go use our point. Question? So the first step here is differentiating both sides. We take the derivative of both sides in this step right here. So I have some stuff to the fourth. The derivative is 4 times my stuff to the third times the derivative of my stuff. Derivative is 3x squared is 6x. Derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. The derivative of 4x is 4. The derivative of 5 is 0. And then after that, instead of, like in the previous problem, solving for y prime, we're going to plug in x equal to the x coordinate and y equal to the y coordinate. And if they're nice, some things will be 0, which is definitely happening here. Then after that, we try to figure out what y prime is going to be. So I have 6 times 2 is 12. Subtract the 4, you get 8. And then 3 times -1 squared is 3 times y prime. So I get y prime equal to positive 8/3. And then to finish this off, we're going to say our equation is y minus the y coordinate equal to the slope times x minus the x coordinate. At least in Grosvenor's class, he does specify that he wants you to write it in the slope-intercept form. So we're going to rewrite this as y plus 1 equal to 8/3 x minus 16/3, right? Distributing the 8/3 to each term. And subtracting 1, we get y equal to 8/3 x minus 16/3. Minus 1 is minus 3/3. So at the end of the day, we have y equal to 8/3 x. And negative 16/3 minus 3/3 is negative 19/3. That's not the only way to find your y equals mx plus b form, but it's the way I like to do it. Interesting. Let me see one thing here. So I'll point out, at least in Grosvenor's class, because he's the one who's giving us some information here. So the last couple things in chapter 3 are last couple topics, I should say, are related rates. You can definitely do an example of it a little bit later. And then the last thing in section 3 or chapter 3 is linearizations and differentials. And I'll point out that that is nowhere on the material covered on the final list for Grosvenor's class. Doesn't mean it couldn't be covered in McDonough's class. I don't know if I feel like we never really talked about it in this class. Did McDonough ever talk about linearizations or okay? Sometimes it gets kind of skipped. It's not important, but it's not that important. So, and then we have chapter 4 stuff, which I'll remind people in Grosvenor's class, he said would be like, right, looking here, reading the thing again, problems from chapter 4 will form the bulk of the final exam. That chapter's practice exercises on pages 292 through 296 offer more practice. He doesn't recommend you try all of them, but he does recommend selecting a random sample and then solving some of them. So yeah, if you're in Grosvenor's class, looks like you should spend some time doing some chapter 4 problems. So here are the chapter 4 topics. We have extreme values of functions. And so when I read this, what it says to me is absolute max, absolute min, relative max, relative min. Those are all types of extreme values. And they're very kind of different in how we find them, right? To find absolute extrema on an interval, say from A to B, step 1, find the critical points or critical values, whatever you want to call it. Step 2, plug each critical value and your endpoints into the original function. So plug each critical value and each endpoint into the original function. I suppose I could say find the critical values of f of x, plug each critical value and each endpoint into f of x. I suppose it bears asking, how do we find the critical values of a function? And what do we do with it? We set the derivative equal to, right? Or potentially also seeing where it's undefined. But yeah, that's how you find the critical values. And then lastly, for this absolute extrema, the biggest y value is the max. The smallest y value is the min. That's it. On the other hand, to find relative extrema, totally different ball game. Typically involving the first derivative test. So find relative extrema, you're still going to start with the critical values. So find the critical values of f of x. But then the second part is going to be use the first derivative test. Derivative test. To classify them. And the picture I keep in my mind is if you've got something that looks like this, where your critical value is there, and your first derivative is positive, then negative from left to right, you're increasing, decreasing, so you must have a relative. And similarly, if your critical point is such that the derivative is negative on the left and positive on the right, then your function is decreasing, then increasing, so we must have a relative minimum. And then if you have anything else, increasing, increasing, or decreasing, decreasing, it's neither a relative maximum nor a relative minimum. It's probably going to end up being an inflection point, but it's definitely not a relative max or relative min. It doesn't have to be an inflection point, but it often is the case that if your first derivative is, if you have a critical point for your first derivative and it's not a relative max or relative min, it often does end up being an inflection point. Okay. And then, oh yeah. So what else do we have here? We have the mean value theorem, which, I'll be frank, it's not easy to ask a good question about the mean value theorem. There is one on Grosvenor's practice exam, which I think we should go over because I think it's kind of nice and not too out of this world. And definitely, you wouldn't think of doing it that way unless you had seen an example of it before. So we'll do that in a minute. Let's finish off this list here real quick here. So mean value theorem. And then we have, I feel like the rest of the stuff I'm about to say, aside from one thing, is just like how you graph stuff. So I'm going to say like 5 things, but it really all falls under the subheading of graphing. So we have the first derivative test, which I know we always just talked about. So first derivative test, and monotonicity. That's just a fancy word for increasing or decreasing, right? A function is monotonic if it's always increasing or always decreasing. We talk about the increasing or decreasing this on different intervals. Someone might ask you if a function is one-to-one or invertible. And a typical way of showing that a function is one-to-one is saying, oh, the derivative is always positive, so the function is always increasing, so it has to be one-to-one. Or the derivative is always negative, so the function is always decreasing, so it has to be one-to-one. So for example, f of x equal to x cubed plus 5x is for sure one-to-one. Here's how we show it. The derivative is 3x squared plus 5. And 3x squared plus 5 is always non-negative. In fact, it's always bigger than or equal to 5, which is for sure bigger than 0. So that means f of x is always increasing because the derivative is always positive. But if a function is monotonic, always increasing or always decreasing, it has to be one-to-one. Each y value only comes from one x value. Or you could also think it passes the horizontal line test. But if your function never makes any turns, right? If I'm always increasing, right, I can never fail the horizontal line test because I never turned around and curved over. Cool. And then we have what's listed on here as concavity and curve sketching. But really, this is all just if you're graphing something, you're finding intercepts, asymptotes, you're finding the first derivative stuff where the function is increasing or decreasing and using that to see if you have a relative max or a relative min. You're finding the second derivative stuff, seeing where it's concave up and concave down, and using that to see if you have any inflection points. And that's kind of the most of the story there. And then lastly, we have, for those of you in Grosvenor's class, L'Hopital's rule. Not going to be on the exam for McDonough. That doesn't mean you don't need to know L'Hopital's rule for 21B. You definitely need to know L'Hopital's rule for 21B. It does come up, not often, but not infrequently. Especially when we talk about improper integrals. For sure, L'Hopital's rule is going to come up. So make sure you have a basic understanding of, oh yeah, we have a limit with a 0 over 0 or infinity over infinity. We can use L'Hopital's rule. Yes, there's lots of other instances where we can manipulate things to use L'Hopital's rule, but those are the two main ones. And then finally, we have optimization or applied optimization, as it says here. Applied optimization, sure. Or just word problems. Which I suppose I could have said for related rates as well. Related rates, also word problems. Different word problems, but still word problems. So if you see a bunch of words like describing a situation, you have to ask yourself, okay, are they telling me that something's changing and asking me how another thing is changing? Oh, that's a related rates problem. Or are they saying you've got some shape and you want it to hold the most amount of liquid it can or have the least amount of surface area? That's an optimization problem. But those are the kind of words to look for to distinguish which one is which. But those are the two main types of like word problems we see. Not that there aren't other word problems, just those are the kind of typical examples. Let me go back and check out that one problem I was kind of referring to earlier, because I do think it's kind of neat. And it's not impossible to do once you know how to do it. So here is the question. So assume that y equal to f of x is continuous and both f prime of x and f double prime of x exist and are also continuous. Or to use less words, f of x is continuous and differentiable and twice differentiable. So here's the question. Given that f of -1 is equal to 0, and the derivative of f of x is always bigger than or equal to 1 for all x. Is it possible that f of 2 is equal to 2? Which feels like a weird question. Let me show you how I'm going to think about it for a second, and then I'll show you with the solution that was written. So here's what I'm imagining. I'm going to draw a little graph. F of -1 is 0. And f of 2, I'm asking, can it equal 2? So from -1, 0 to 2, 2, what's the slope of the segment that would connect those 2 points? What's my rise? What's my run? What's my rise? What's my run? Cool. So my slope is 2/3. So now here's where the mean value theorem is going to come into play. The mean value theorem says that between these 2 points, there has to be a place where the derivative is equal to the slope of the secant line. Or in other words, there has to be a place where the derivative is equal to 2/3. But we have made the problem has made the assumption that the derivative is always greater than or equal to 1, which means there isn't any way the derivative could ever be 2/3, which means there is not the possibility that this function could equal 2 at 2. Because so let me write out so that's kind of what I'm thinking, but let me show you the argument. So here's what we're saying. If f of 2 is equal to 2, then by the mean value theorem, there must exist a number c between -1 and +2. Right, so here's maybe c lives right here. And maybe the function looks like this, where or such that the derivative at c, or the slope of the tangent line at c, is equal to the slope of the secant line. It's equal to f of 2 minus f of -1 over 2 minus -1. That's the mean value theorem. And we know we can apply it because we have met all the conditions. We were told the function was continuous and differentiable everywhere. That's all you need to be able to use the mean value theorem. Continuity and differentiability. But then look, this means that f prime of c has to equal f of 2 minus f of -1 over 3, which is 2/3. But 2/3 is less than 1. And we were told that the derivative is always bigger than or equal to 1. So that's a contradiction of what we assumed was true. So under the assumption that f of -1 is equal to 0 and f prime is always bigger than or equal to 1, it is not possible that f of 2 could equal 2. So this is, in my opinion, one of the better questions someone could ask about the mean value theorem if they wanted to ask it. It's not too far out there, but you do have to kind of have seen an example of it once before to kind of have the idea of what to do. I have no clue whether McDonough might ask something like this or not. My guess would be probably not, but it doesn't hurt to have seen it anyway. Okay, so that's the list, and it's not a short list of the things you need to be aware of for your final. So now I think we should spend the last, 20 minutes we have here talking about some optimization problems because we didn't really do much in the way of optimization. I feel like we did a little bit, but not a lot. Yeah, we did some in this class, right? I feel like we did, we did like some box ones, and we did like a cylinder, we did a box, and we did something else. Sure. Did we do a cone? Maybe. Let's do a cone. So let me give you a couple other typical optimization problems. That'll be it. So some more optimization examples, because certainly I also did note in McDonald's notes that he did say that optimization would probably be on the final. Right? He said no L'Hopital's. He did like one L'Hopital's example. And then he said optimization and started an example and said it would probably be on the final. So let's look at some optimization examples. Like, for example, I'm trying to think of examples that are reasonable, not that crazy. Sure. Cone. Is there a cone problem? Oh, there's that kind of cone problem. Okay. So yeah. Sorry, I need to look here. Coming up with these problems is always challenging. One sec.
After we do optimization, can we do number 6 on the practice?
We can do number 6 right now. We don't have to start with optimization. Which one is number? This is on Grosvenor's class.
Yeah, it's not like
Sure. Oh yeah, this one looked challenging. Let's take a look. So, ooh, yeah, all right. So here's the setup. A runner is running on a straight trail of length 7 miles. So I'm gonna draw the picture that he has drawn for the problem. So you've got a trail from A to B, 7 miles long. And you've got your runner right about here, and they're running that way. And point P is located off the trail. It's closest to point A on the line. AB is 3 miles away. So here's P over here. And that's a 3 mile distance. And similarly, Q also over here, 4 miles away from B. Cool. And then they say, at some time, the distance between the runner and A is 4 miles. At some time, the distance between the runner and A is 4 miles. Okay, sure. At the same time, the distance between the runner and P is increasing at the rate of 8 miles per hour. Find the following rates at this instance. Oh, Jesus. Wow. Okay. So let's say that the distance the runner is from A is X. And after we do all the whatever related rate stuff we're going to do, after we've differentiated both sides, we're then going to plug in X equal to 4 because that's what they're telling us. At least I think that's what we're going to do. That seems reasonable. Yeah. And then, yeah, the distance between the runner and P. So that's this here. And let's call that R to be consistent with what they have used in the problem. So here's what we're given. We're given that the distance between the runner and P, which is R, is increasing at the rate of 8 miles per hour. So dr dt is 8 miles per hour. And at that same moment, this is true when X is equal to 4 miles. And they're being asked to find, at least in part A, the question is how fast or what is the velocity of the runner? So what are we being asked to find here in terms of derivatives? D what, D what? Well, what variable is representing the position of the runner? Or how many miles they've run? I mean, there's only one other variable. I know there's a lot of letters on this picture. There's only one other variable other than R. X. X is how far they've run. So dx dt is what we're trying to find. That is the velocity of the runner. So now that I've identified the thing I want to find and the rate I already know, I'm going to try and write an equation involving just those two variables. I would love an equation involving just x and r and nothing else. So I see a right triangle. I'm going to say that x squared plus 3 squared equals r squared. And I do not love the way he is doing this in the solutions. So in my, and I also talked to my friends, like I talked to other people I work with, they're also like, why would you do it this way? Not that we looked at this one, but like there's another problem where, so in the solutions here, let me just show you. Right. He has done something that I think is unnecessary. He's taken the square root of both sides and then differentiated. But you don't have to do that. And it's not really saving you any work. So what we should do instead is not that. Can I differentiate both sides of this as is? For sure. What's the derivative of x squared? Times dx dt. What's the derivative of 3 squared? Everybody. Thank you. What's the derivative of r squared? Times, right? For these implicit differentiation problems or these related rates problems, oh, by the way, they're implicit differentiation problems. You're always multiplying by the derivative of your stuff, right? I have some stuff squared. Its derivative is 2 times the stuff times the derivative of the stuff because x isn't a function of x is a function of time. Similarly here, the derivative of r squared, or if you like, r of t squared is 2 times r of t to the first times r prime of t, or if you prefer, 2 times r times dr dt. And now that we've differentiated both sides, now we're going to plug in. We're going to plug in that x is 4, because they told us that. We don't know what dx dt is. That's what we're trying to find. We're going to plug in that r is, well, I don't know what r is yet, but I know that x is 4. So if x is 4, then 4 squared plus 3 squared equals r squared. 4 squared plus 3 squared is 16 plus 9, which is 25. So r is going to be 5. And then dr dt was given to us. That's 8 miles per hour. So then solving for dx dt, I get dx dt is equal to 2 times 5 times 8 divided by 2 times 4, which is going to be 10 miles per hour. Yeah, which is way easier than the way he's doing it. So I really can't stress enough. If you're doing a related rates problem and you have like some Pythagorean thing, don't introduce square roots. I don't think it's ever necessary. It certainly isn't wrong, but it's creating more challenging derivatives to look at. Okay. The next question is how fast is the distance from the runner to Q changing? Let's call that S. Before we write down the answer here, do we expect S to be increasing or decreasing as we move up? Right, so we expect ds dt to be positive or negative. What was that? If S is decreasing, we expect ds dt to be negative. Right, if something's getting smaller, its rate of change is negative. Okay, let's see what happens. So I'm going to do the same sort of thing. I'm now trying to find, and the problem is, so the problem is find the rate of change of the distance between the runner and the point Q. So they're asking us now for part B to find ds dt at the same moment when x is equal to 4. Okay, so I want an equation involving x and s. So I see another right triangle. You don't see it though, because you can't see my picture there. I see another right triangle where I have this side here, which is 4, plus this side here, which is not x. This side here is 7 minus x. So 4 squared plus 7 minus x squared equals the hypotenuse squared. I want to find dSdt. I know from the work we just did that dx dt at this moment is 10 miles per hour. I would like to find dSdt. I suppose I should admit here, I got ahead of myself. I should have written down this part first if I'm doing it the way I usually do it, which is I say, okay, here's what I know, here's what I want to know, and then I try to get an equation involving those variables. That's the more straightforward, or the more typical way I usually do this. So now, just like before, don't take any square roots. Differentiate this as is. We differentiate both sides. Derivative of 4 squared is 0. The derivative of some stuff squared is 2 times my stuff to the first times the derivative of the inside, and the derivative of negative x, be careful here, it's not just -1, it's negative dx dt. Equal to the derivative of s squared, which is 2 times s to the first times ds dt. We are hoping to figure out what this is, which means we need to be able to plug in for everything else. We know that x is 4. We know that dx dt is 10. We need to know what s is. So I'm going to go back to my equation. This plus this equals that, and plug in the value of x being 4 to find the value of s. And I'm pretty sure it's going to be another 3, 4, 5 right triangle, because you're going to get 4 squared plus 7 minus 4 squared equal to s squared. But that's just 16 plus 7 minus 4 is 3 squared is 9. Oh yeah, s squared ends up being 25, so s is 5. So that's going to be 5. And then we can solve for ds dt. So we've got that 2 times 7 minus 4 times negative 10 equals 2 times 5 times ds dt. I have a 10 there and a 10 there, so they kind of cancel. So you have 2 times 3 times negative 1, so negative 6 equals ds dt. So ds dt is negative 6 miles per hour. Again, it makes sense that it's negative because the length s is getting smaller. Yeah, but definitely don't use square roots if you can avoid it. And you definitely can for related rates problems almost undeniably all the time. That's really interesting. I'm curious. I'd be curious to talk to him and ask him like why he is thinking of it that way. Maybe that's just the way he learned it when he was a student, and that's all, right? Sometimes you learn something one way, and that's just the way you always do it, even if there's another way that might seem easier to other people. His way is not wrong, it just feels more challenging. So now with 6 minutes left, can we get an optimization problem in? Maybe. What's that? Let's take a look. Oh yeah, that's a good problem. Sure. Yeah, I like that. I feel like this feels like the right level of difficulty for an optimization problem to me. Some other shapes or situations are get more complicated, but I think this problem is pretty good. So here's the setup, and I'm not going to try and write all the words because 5 minutes. So I'll read the words, I'll write the important things. A construction contractor needs to build a small rectangular storage box with a square base, flat roof, and volume 16 cubic feet. So here's what we've got. We've got a small rectangular box. And they've shaded in the roof like this. So the flat roof. Thank goodness, because a different shaped roof would be harder to deal with. We know it's a square base, so we're going to call each of these lengths on the bottom x because they have to be the same if it's a square base. And then we're going to call the height of the building y because it's not necessarily the same as that. We want the volume, so the volume should equal, well, the equation for the volume would be x times y. And they're telling us we want this box to hold 16 cubic feet. And then we are also told every square foot of sidewall costs $1. So sidewalls cost $1 per square foot. $1 per square foot. And every square foot of roof costs $4 per square foot. Wow, can I write the 4 maybe? Assume the base does not need to be built, so it costs nothing, which seems like a stupid assumption, but I understand why you would do that. Not a real life assumption. Okay, so find the dimensions of the box that will minimize the building costs. Be careful when you read this question here. Make sure you're answering the right thing. So sometimes the question, more times than not, the question will be find the dimensions that minimize or maximize some value. Occasionally, the question will be find the minimum cost or find the maximum whatever. So not just finding the dimensions, but finding actually the output you get when you plug those dimensions in. Usually it's the dimensions, but just be careful. So we've got our volume, which I don't usually write first. I should say we've got our constraint, which I don't usually write first. Some equation equal to a number. And then the thing we want to minimize here is cost. So we're trying to minimize cost. So the cost equation is going to be, well, the top roof has an area of x squared. And the cost for 10 square feet would be $40. The cost for x squared square feet would be 4 times x squared dollars. Right? Each square foot on the roof costs $4. If there are x squared square feet, then it's going to be a cost of 4 times x squared dollars. Or essentially, you multiply your area by whatever the rate is. Similarly, for each side, x times y, the cost is going to be $1 per square foot. But there are 4 of those sides. So those 4 sides together are going to cost 4 times x times y. The area for xy times the cost of $1 per square foot. And that's our cost. Notably, the thing you're trying to minimize or maximize does not get to be set equal to a number. If it was, that would be the value that it was equal to, and we wouldn't be looking for a minimum value. So then we have a thing we want to minimize. It has too many variables in it. We use our other equation to rewrite this as a function of one variable. So I'm going to take this constraint and I'm going to solve for the easier thing, which is y. So y equals 16 divided by x squared. I'm going to plug that in over here. I'm going to get cost as a function of x, not that you need to write that, as 4x squared plus 4x times 16 divided by x squared. It is definitely in my interest to simplify this before I differentiate. I'm going to write this as 4x squared plus 4 times 16 is 64. X divided by x squared is x to the negative 1. Take the derivative, get 8x minus 64, x to the negative second, equal to 0. For solving these, I feel like the rules, I pay less attention to the rules than I might usually, but the right way to do this is to write it as 8x minus 64 over x squared equal to 0, and then multiply this by like x squared over x squared to get 8x cubed over x squared minus 64 over x squared equal to 0, and then factor out and say we've got 8 times x cubed minus 8 over x squared equal to 0. So the critical value I'm going to get is going to be x equal to 2, because 2 cubed is 8, and 8 minus 8 is 0. 0 is not really a critical value here because it's not in the domain of the original function, right? X can't be 0 here because you'd have division by 0. X also can't be 0 because if x was 0, the volume couldn't be 16. So what I'm really doing is I'm saying x cubed minus 8 has to equal 0. But then x cubed equals 8. So then x equals the cube root of 8, which is 2. And then we're typically supposed to check to see that you're actually getting a min or a max if you're asked to find a min or a max. So here, to check that it's actually a minimum, there's 2 ways of doing this. At least 2 ways. Yeah. There's the second derivative test. You can say that C double prime. And I know we're over time, so I should wrap it up here. So C double prime is 8 plus 128 x to the negative third. If you plug in 2, you get 8 plus 128 over 8. I don't really care what that is. I care that it's positive. So the second derivative is positive. That means we're concave which way? If we're concave up, do we have a minimum or a maximum? Right. So if C double prime of your critical point is positive, that means we're concave up, which means we have a minimum at x equal to 2. Then we go back and we find the y value. So you go back and you look at your equation and you look for where you have y already isolated. You great, x equals 2, y equals 16 over 2 squared, which is 4. So the dimensions here are x equal to 2 feet, y equal to 4 feet. And that's going to minimize your costs and still give you the right volume. Interesting. I'd be happy to talk about part B in office hours since it is 2:32. All right. Next week I'm available in drop. I think I said this already, but I posted on Canvas already. I'm in drop in Monday through Thursday, 10 to 2, sorry, 10 to noon, 1 to 3, except for Monday from 11 to 12. Yeah, look on your finals. I hope they go well.